So this video is to show you a little bit about how to do controller design using some of the tools in Matlab. So I'm starting with the example that I started in lecture 25. So here is the plant, GP, looks like this, S times 1 plus S, blah, 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 you can read the rest. And the design specifications is for a unit step disturbance, the steady state error should be less than or equal to 1%. And I want the percent overshoot for a step input to be less than 25%, okay? And so the calculations I did here says that I need about a 43-degree phase margin to meet the overshoot. And remember, the idea is disturbance to error. The disturbance is coming in here, D, and error is over here. And I calculated, I wrote on lecture 25, I wrote that transfer function E over D, transfer function from disturbance to error, is minus GP over 1 plus GPGC. Okay, so that's the transfer function I'm going to use to calculate the error. And if you look back at this lecture, it turns out that I need a gain of 100 to do that. So this controller, I started out with just a simple proportional controller. Here, that's what this says here, GC is equal to K. I started out with a proportional controller here, and I calculated the gain has to be 100 to meet the steady state error specification. Okay, so that's how I'm going to start the design. And then if we look back to my lecture 26 here, I did a phase lag compensator, okay, and the phase lag compensator, I'm not going to go through the calculations because these are in the notes. I calculated the parameters A should be 10 raised to the minus 37 over 20, and the other parameter T should be 708, okay? So now I'm just going to implement those things in Matlab, and let's see how that. Okay, so here's the Matlab code that I wrote, and I guess I'll post this to the smart side as well. So I'm defining the plant GP, and this is the same plant. Like if you look at it, it's the same as the plant from the lecture. And then the controller, well, I set the gain to be 100. K is 100. Here's A, and then here is T, and it turns out T is 10 over A. And so then when I implement the actual controller, it's GC is equal to K times 1 plus A times T times S divided by 1 plus T times S. Okay, so that's the phase lag compensator. And then I form some closed loop transfer functions. So from reference to output Y, that's GR to Y. Okay, that's GPGC over 1 plus GPGC. And then from disturbance to error, GD to E is minus GP over 1 plus GPGC. So this is the same transfer function that I wrote in the notes. Okay. Now, I ran a step simulation for a step disturbance. So I simulated it for 80 seconds, and so that's what this TF here is, the final simulation time. And then it says ET is equal to step G D to E until the final time. So this is the error, and this is time, and I'm going to plot all that stuff out. So the first plot I plot is margin of K times GP. So that's the phase margin of the uncompensated plant. So I have to multiply it by the gain that I calculated. Okay, and then figure 2 is the compensated plant. So margin GP times GC, and K is incorporated into the controller here. You see K is in the controller. So I'm plotting those phase margin plots, and then I'm going to do some step responses. So figure 3 is the step response from reference to output Y, GR to Y. And figure 4, I plotted the error that results from a step disturbance. And I generated it this way because it turns out the simulation didn't run long enough for you to see the steady state error. And I just wanted to show you that that actually works. So here, let's go, and I'm going to run it. Oh, let's see. Funny how that works. Okay, so I clear everything, and then I'll run it. Okay, and the plots should sort of appear one by one here. Remember, the top two are going to be the phase margin plots. First one is the uncompensated phase margin plot, the uncompensated Bode plot. The second plot here is for GP times GC, so this is after compensation. And then I have the two step response plots. So the step response plots for the reference to the output, and then over here it's the step response from disturbance to error. And the first thing I'll show you is that, and so these ones here on the bottom are for the compensated closed loop. I didn't bother plotting the closed loop with the uncompensated plant because the phase margin here is negative, so this thing is actually unstable. So you see before compensation, it says here phase margin is minus 1 degree. That's not good. I did some compensation, and if you look over here, it says phase margin is 38.6 degrees. And so how did I do this? Well, what I did was I forced the transfer function to cross through 0 dB at a point where the loop has about 45-degree phase margin. So I could pick that off, like over here. I'm going to look for to have 45 degrees. I've got to look for where the phase goes through minus 135, because that's minus 135 is 45 degrees away from minus 180. Okay, so that's at about 1 radian per second. And if I mouse along here on the gain plot at 1 radian per second, you see that it has a gain of 37 dB. And that, if you remember from the lecture notes, is exactly how I calculated the parameter A from my controller. So what I wanted to do is I want to force the gain crossover to be at 0 dB at about 1 radian per second. So let's look how I did over here. This is the compensated response. And again, I can sort of mouse along here. And you see that it is at, let's see, it's very hard for me to get to 0 exactly. But basically, it's 0 dB at 1 radian per second. So I made the crossover happen where I want it to happen. And now it's showing here is the compensated phase margin. It says it up here. It's 38.6 degrees, so that's pretty good. Okay. Now I can come down to the step response. Remember, the two parameters that I wanted was I had steady state error, and that's over here. So I need that to be below 1%. And so let's zoom in. This runs for 80 seconds. So if I zoom in here sort of at the end, I can see that indeed here's the response, and it's at 0.01. That's 1%. So it gets to 1%. It takes a long time to get there, 80 seconds to get there. But indeed, I do meet the steady state error specification. There's nothing that says in the specs about when I have to get there. It does meet the specs. And then over here, I needed less than 25% overshoot. So I can right-click here, and I got characteristics, and I can do peak response, and it'll pick it off here. And I can click on it. It's 1.35. So I have 35% overshoot. So I didn't quite meet the specification, right? So the problem I have is I don't have enough phase margin. So I did all this stuff sort of manually, and that works fine. I'm going to close these plots. But I want to show you, so to revise the design, it may be a little bit easier to use a tool called the sisotool, and hopefully it will run quickly. So the sisotool does everything that I just did, but it does it like it kind of generates the plot sort of automatically, and it allows you to do a little bit more interactive design. So I typed sisotool in the command window here. And it starts out with, you see there's some windows here that has a root locus. It's got open loop Bodhi plot here, and it's got a closed loop Bodhi plot, which we haven't really used that very much. We're really going to be looking at the open loop Bodhi plot here. It's got gain and phase. And then here is the control and estimation tool manager, and it shows me the architecture that I've got. So C is the controller and G is the plant. And in our case, H is going to be 1 and F is going to be 1. Okay, so what do? The first thing I can do is it says system data. I click on this, and then it tells me, okay, G, right now it's a 1, and what I can do is browse, and because I already have these, they're in the workspace right now. So my plant, I want G to be the plant here. I called that GP, so I'm going to import it, okay, and then I can go to the controller C, and I go to GC and I import that, and I'm done. Okay, so now I have the system G is equal to GP, that's how I defined it, and the controller is GC, and I just click OK. And now those transfer functions that I defined are going to be they're going to be entered into it here, and I'm going to move this down. And now I've got my open loop Bodhi plot, and it shows me the same information that I had before. It's got if I look down here, I've got a 38.6 degree phase margin at 1 radian per second, and here's the gain margin 34 dB, and it says stable loop, so it's stable. I'm just going to ignore the root locus. I'm actually not using it here, and I'm not going to use the closed loop Bodhi plot either. The other stuff that I can use here is I use an analysis plot, and the analysis plot would be if I want to do like a step response. So let's do the closed loop step response from reference from R to Y here. So I click that, and plot 1 is going to be my step response plot, okay? And then I do show analysis plot. And it'll come up, and it'll show me basically the same step response that I had here, LTI viewer, and it says real-time update. So now as I change the controller, this thing is going to change automatically, okay? And I can right-click here again, and characteristics, I can do the same thing, peak response, and it comes up here, and it's the same thing. So I've got 35% overshoot. It's too much overshoot, and so what I got to do is I have to fix that somehow. Now there's a couple ways to do this. One way is sort of the manual way, which is that I know what I need is I need to get a little bit more phase margin. And so I can go back into the design and I can retarget for more phase margin. The other thing this allows you to do is, I'm going to make this smaller, is these are actually the, it says here, if you look down here, it'll tell me as I mouse over this 0 here, it says left click to move this 0 of C. So this is the controller 0, and then this pole here, left click to move this pole of C. So that's the controller pole. And so I can actually sort of mouse along here, and I can change those. And so as I drag that along here, so I made the phase margin worse by pulling that back. That's not a good thing to do. So if I sort of move it along this way, now I have a 40-degree phase margin. If I move it a little bit more over here, I got 41 degrees. That may or may not be enough. But the nice thing is that it sort of automatically adjusts the step response. I can see it's got like 36% overshoot. So far it's not working out for me. Just moving these things around is not a good way for me to do this. I think I can probably pull them back a little bit, and I may be able to. Well, so I think from just goofing around with this, I'm not going to be able to get it to work just by manually trial and error here. So let's give up on that. I wanted to show you that it could be done, but there's actually a better way to do this optimization. So I'm going to go back to the window for the tools here, and I'm going to go back and I'm going to re-import. I go back to the architecture, system data. I'm going to re-import my controller. So I think, let's see, just check it. So here's GC, import. I think, let's see, I close that and say OK, and it should just get everything back to where it was before. OK, so now everything's back to where it was before I started messing around, 38.63 phase margin. So it turns out there is automated tuning available, optimization-based tuning. And so now what I've got to do is I have to, it says specify design requirements here, and I can do optimize compensators, and this should work. There it goes. Okay, response optimization, initializing data. Okay, so the first thing I've got to do, it says select compensators to optimize, select design requirements, set the optimization options, and then optimize, and then see what it does. So if I go to the compensator here, it's got, here's the elements that I can change. I want to leave the gain alone, but I want to change the pole and the 0 of the controller. Okay, so those are the two things that I'm going to optimize. So it says basically, I've checked the ones that I want to optimize. Design requirements here. Okay, add new design requirement. So I want to optimize based on the step responses. New design requirement here. Step response bound. Closed loop from R to Y. And what I want is I want the overshoot to be no more than 25%. Okay, and there I go. That's the only bound that I care about. Okay. And it will enforce that one. And actually now, if you look at my little step response viewer here, it's got the bounds on there. So now you can see, here's the 25% overshoot bound, and you see how much my existing compensator has exceeded that bound. And now what I can do is do the optimization, and I can start it, and it will just automatically iterate. It'll take a little while here. It says constructing optimization problem, and it'll start basically, it will iterate through by changing the controller pole and 0, and it's running the optimization, and it will run through a few cycles, and each time it does the optimization, it will show me the resulting response. So it made it a little bit worse here, now it made it a little bit better, it's getting close now. Oh, and there it met it. See, look, now it's met the response, and we can actually look over here and what it did to the phase margin. So now it actually has a 53-degree phase margin here. So more than the 45 degrees than I thought I needed, and the step response now meets the specs. So this is a cool way to be able to do automated optimization, and obviously this is not necessarily the way I want you to do your homework, but it's a very powerful tool to use for real control system design. Bye.